All right, so the addition and complement rules. 12.4, and this is our last section in 12.4. Last section in chapter 12, section 12.4. Starts off talking about mutually exclusive events, events that cannot occur at the same time, or events that do not have anything in common will be considered your mutually exclusive events. The way we would calculate the probability of mutually exclusive events, we have the probability, we want to know the probability of event A or B. You would just find the probability of A and add it to the probability of B. All right, so before we go to the first example, I want to make sure we establish when it says standard 52 card deck, what does it mean? So when it says standard, it means no jokers. So in a standard 52 card deck, there are 4 suits: clubs, spades, hearts, and diamonds. 2 black suits, or 2 sets of black cards, I guess you could say. 2 black suits, clubs and spades. 2 red suits, hearts and diamonds. 13 cards each suit. 4 times 13 gives you that 52. You have 10 regular cards and 3 face cards. Your 3 face cards are your king, queen, and jack. And your 10 regular cards, ace, and then 2 through 10. All right, let's look at the first problem. This is something. Give me one second. All right, I had to get this pen. All right, let's get back to it. So suppose a single card is drawn from a standard deck of playing cards. Find the probability of drawing a 5 or a king. So what we have here in the red is the questions, or the question that you want to ask yourself. Are your events mutually exclusive? And in this case, they are. They have no cards in common. There's no such thing as a king of 5s or a 5 that is a king. So they are mutually exclusive. They do not have any cards in common. So looking at your first event to draw a 5. Our sample space is 52. We have 52 cards in the deck. The number of 5s. The number of 5s that we have. There are 4 5s in the deck. 1 out of each suit. And so place that 4 over 52. That will be the probability of getting a 5. Same thing happens for drawing a king. There are 52 cards in the deck. Total number of possible cards. There are 4 kings in the deck. King of queens, king of hearts, king of clubs, king of spades. That's a king of queens. King of clubs, king of spades, king of hearts, king of diamonds. So there's 4 kings in the deck, just like there are 4 5s in the deck. Then you place that 4 over 52. And that's the probability of getting a king. So now if you want to find the probability of getting a 5 or a king, take each one of those probabilities and add them together. So notice I reduced at the end and then reduced in the middle of the process. It'll help you out in other things, other processes that you go try to carry out. So I always say just reduce at the end when it comes to adding and subtracting your fractions. But 4 over 52 plus 4 over 52 is 8 over 52. And both of them have 4 in common, or you can divide each number by 4, and that'll give you 2 over 13 as your probability. Questions on that one before we go to the next one? All right. The general addition rule, probability of A or B occurring. You do the probability A, probability B, so you add those together, but then you're going to subtract what they have in common. Probability of A and B is what they have in common. So if they're not mutually exclusive, then they will have something in common, and you're going to subtract what they have in common. So when we look at the next example, we'll see why that is the case. All right. So we have a single die that is rolled. Find the probability of rolling an even number or a number greater than 2. All right. So we have 2 events here. One is an even number. The other is a number greater than 2. So if we look at an even number, we know our sample space from dealing with a single die before is 6. We have 1 through 6. So an even number that is in that set, that sample space, is 2, 4, and 6. So we have 3 even numbers. So place that 3 over 6. So that's the probability of getting an even number. The other event, a number that's greater than 2. Once again, our sample space is 6. 6 possible numbers, 1 through 6. Numbers that are greater than 2, 3, 4, 5, and 6. So the 4 numbers that fit that criteria. So 4 over 6 is our probability of getting a number greater than 2. All right, so now if I were to add just those two together, you'll realize that you'll get 706, which is greater than 1. Remember, we said our probabilities are supposed to be in between 0 and 1. So that wouldn't work for us. So something has to be going on. But notice that in our probability, not in our probability, in our events, 4 and 6 are being counted twice. When I look at 3 over 6, I'm counting 4 and 6. And then when I'm looking at the 4 over 6 here, that is counting the 4 and the 6. So this is why you have to subtract what they have in common, because you're counting what they have in common twice if you don't do that. So we look at what they have in common. Is it possible to be even and greater than 2? The answer is yes. And that's 4 and 6, like we already mentioned. So we have two numbers that are even and greater than 2. So that probability would be 2 over 6. And that means now we have all three pieces to be able to complete the formula. So if I want to know the probability of getting E or G, remember E was an even number and G was a number greater than 2. I will I'll add the probability of E plus the probability of G, and then subtract the probability of them together, and I get get 5 over 6 as my final answer. Questions, questions, questions. All right, let's go to the next one. In the table, the data shows the results of an experiment conducted to test the effectiveness of a flu vaccine. If one person is selected from this population, what is the probability that the person was vaccinated or contracted the flu? So I'll give you a chance to write that before I scroll down. All right, so here's the table. Let me erase. So V represents the vaccinated, F represents those who contracted the flu. So that 21 represents those who are vaccinated and contracted the flu. 198 vaccinated with no flu. 219 are the total number of those who were vaccinated. Then you have 76, no vaccination but contracted the flu. 195, no vaccination and no flu. 271 are those who were not vaccinated. And then you see your total numbers down bottom. All right. So that 490 is our sample space. That's the total number of possible outcomes, total number of people that are being what they surveyed. Just an experiment. People that participate in an experiment. So that's my sample space, 490. So now I want to figure out the probability of selecting someone who was vaccinated or contracted the flu. So I need the probability of vaccinated people, probability of flu contracted people, then I need to subtract what they have in common. So the 490 is going to be on the bottom of each. So we look at 219. That's the total number of people that were vaccinated. The contraction of flu is 97. Is the total number of people that contracted the flu. And then what they have in common is this 21. And so that's how I did or set up my formula. 219 over 490 plus 97 over 490 minus 21 over the 490. Questions, questions, questions. And then WebAssign will let you know which version of the answer that they want, whether it be the 295 or the 490. You know, I have to add 219 and 97, then subtract 21. Or convert it to a decimal, you know, with approximately 0.602. All right. So the complement of an event. I believe it's the last thing or the last new topic in this section. The opposite of the event would be considered a complement. That would be all elements in the sample space that are not in the event. So, and then if your event is E, then E with that superscript C, and that circle is not there for the notation. I was just using it to emphasize what I was talking about. So that E to the superscript C represents the complement of event E. So a small example, if my sample space is 1 through 6, if my event is 1, 2, 3, that means my complement or the complement of that event will be 4, 5, and 6. All right. Questions? Any questions? All right. So the probability of the complement. So the relationship it has, if you're looking at the probability of E to the C or the probability of the complement, you would do 1 minus the probability of your actual event. Or if you had the probability of your event, or if you wanted to find the probability of your event and you had the probability of the complement, you can subtract that from 1. Or if you have both of them, when you add them together, they should equal to 1. So all of those are the same relationship, just solved a different way or manipulate a different way to be able to solve for whatever it is you're looking for. All right. So the probability of tossing a sum of 11 on the toss of 2 dice is 1 over 18, or 1 out of 18. What is the probability of not tossing a sum of 11 on the toss of 2 dice? All right. So the probability of the complement is what we want to know, because we want to know the probability of not tossing a sum of 11. So we know the probability of tossing the sum of 11. We want to know the probability of not tossing the sum of 11. So we do 1 minus the probability of that, which is 1 over 18. And to do your fraction work, that 1 is going to convert into that denominator over itself. Because remember, in order to add or subtract fractions, you need a common denominator. So 1 with a denominator of 18 is going to be 18 over 18. So 18 over 18 minus 1 over 18 will give you 17 out of 18. So my denominator down here was a 5, then that 1 would turn into 5 over 5. So whatever that denominator is, that 1 will turn into that over itself. All right, any questions? Right here, the probability that a person has type A blood is 34%. What is the probability that a person does not have type A blood? So 34% is a probability that a person has type A blood. As a decimal, 34%, that 0.34. So you subtract that from 1 to figure out how many people, not how many people, but the probability of not getting someone who has that type of blood. So it'd be 1 minus 0.34, which would be 0.66 as a decimal, or 66%, depending on how they want to answer. Any questions? Any questions? All right, I think this is the last one out of the section. Yep. All right, a die is tossed 4 times. What is the probability that a 6 will show up at least once? All right. So we have to establish our sample space first, as always. So we have a die that is tossed 4 times. So I create my 4 boxes that represent each time that the die is tossed, and each time we have 6 possible options. So that's why the 6 is in each box. Multiply all of those together, you get 1296. There are 6 options total, so that's why there's 6. The number 6 in each box. So every time I throw the dice or toss the dice, toss the die, not 2 dice, but every time I toss the die, I have 6 possible numbers that could occur or show up. So you multiply your options, the total number of options in each slot. All right. So the event we're trying to calculate is, or the probability we're trying to find is at least 1/6. So it would be easier for us to find the probability of no 6s occurring. So the way we would look at this, so the probability of no 6s occurring is taking each one of those boxes and putting a 5 there. So there are 5 numbers that are not 6. So what's the probability of getting one of those 5 numbers? So in each box we put the 5 options, 1 through 5. So 5 times 5 times 5 times 5 is 625. Place that 625 over that 1296, the sample space. And now we can subtract that 625 over 1296 from 1. So 1 minus 625 over 1296. Remember I mentioned before that 1 would turn into the denominator over itself. So it's 1296 minus 625 in your numerator. So it's 671 over 1296, or 0.518. Once again, that depends on what Weber sign is asking of you as far as the form of your answer is concerned. All right, questions? All right, so that closes us out for chapter 12. We have chapter 13 left to knock out. Make sure you're trying the stuff out, getting your work done. If you have any questions, always feel free to email me. I will post the review and test for chapter 12 sometime between today and tomorrow. And so take a look at this stuff. I'm going to always open the floor for questions first. If you guys have them, you can bring them to class and we can discuss them. Most definitely your questions could benefit your classmates as well. But if you don't want to wait until class time, always feel free to email me. And we'll go from there. Any questions, concerns, or comments before we close out for the weekend? Everybody good? Everybody all right? All right. Sounds good. Sounds good. All right. Well, if you guys are good, I'm good. I will see you guys on Monday. Have a great weekend.